Okay, hello everyone. We will be finishing off Tutorial 4, and I hope you have already gone through my video about Ukkonen's algorithm before you look at the current video. So we have pretty much covered question 4 and question 5 in the previous video, which I explained what Ukkonen is, and I somewhat explained very briefly from a conceptual point of view why your Ukkonen is linear at O of n. Okay, so when the tutorial's answers are released, you can look at a more formal mathematical explanation, right? But once again, I'm not here to be giving you your answers, right? I'm not here to solve it. I'm just helping you to understand what is happening with your tutorials and hopefully help you understand your tutorial answers. Okay, so we are only left with question 1, question 2, and question number 3. Okay, question 1 and question 2 is somewhat similar. Okay, when if you were to look at all of your past years exam about Ukkonen, you're always given 2 questions for Ukkonen. So it's usually, for example, question 3 or question 2, A and B. Okay, the first part of your question A is always to draw out a tree, right? As what I mentioned in the past, in 2004, if you're from the older batch, or if you ask your seniors in 3155, Harun, your chief examiner, loves trees a lot, right? And as some of your juniors have realized from some of your internship as well, trees are commonly used in a lot of the companies. So because trees is very important, right? It's very popular. Harun, for my belief, always like to ask questions about trees, right? And some of his common tree question is build a tree, draw out a tree. It can be a suffix trie, prefix trie. It can be a B tree, which we have not learned yet. It can be a red-black tree, which is not part of your syllabus anymore. It can be your self-balancing tree, right? It can be binary search tree. It can be any trees, okay? And so question 1 is just a very simple question, right? Given the following string, draw out your tree, right? Here it just mentions suffix trees, right? And their corresponding implicit suffix tree. So when it is implicit, it means your dollar sign doesn't exist, right? So make sure you read your question very carefully for your exam. If we mention explicit, make sure you have your dollar sign. If we mention implicit, your terminal character is not required. So question 1 is very simple. When the answers is out, you can double check your answer on your own. It's so simple, I won't go through it. So in return, I'm going to do question number 2. I'm going to expand question number 2 as much as possible, and I'm going to link it up with all of the problems in question number 3. Okay, in other words, I skip question number 1, right? Because if you can do question number 2 on your own, you can definitely do question number 1. It's just pointless. Okay, and for question number 2, instead of only implicit, I will also include an explicit of the tree. So if you remember from Ukkonen, you draw out an implicit tree first, you grow your implicit tree, and once you grow your implicit tree, put it in your terminal character, convert from implicit to explicit. At the same time, I'm going to include your suffix link. Okay, in your past year exam, suffix link always appear in every question about Ukkonen, right? So suffix link is very, very important. You should be able to draw out your suffix link, okay? And I've also noted something, right? Your exam question usually do not require you to draw it step by step, right? It's just about drawing your final tree. Because as long as you can draw out your final tree, it will usually be correct. Okay, but the suffix lim part is usually very, very tricky. But since your exam is most probably going to be an open board exam, okay, I'm not sure if your exam question will now want you to draw it step by step. Okay, in fact, I'm having a feeling you may be asked to draw it step by step because it's going to be open board and the steps as you go through will be much more important from now on. Okay, so and once I draw out the tree, I'm going to use the tree to solve every problem here. Okay, so let us begin. Okay, so let me just copy your string first. Okay, string equals to A B C A B A. Okay, A B C A B A. Okay, so let's change to my whiteboard. Now, in order to test your understanding, right, before you finish off the rest of the video, I would like you to draw out the tree on your own, right? Give it a try, follow it step by step, right? And see if you're able to draw out the tree on your own. It's going to be a very, very good practice on your own. Okay, so let me put some numbers. 1, 2, 3, 4, 5, 6, 7. So in my explanation, I'm going to go through all three of your rules. Okay, right, rule 1, 2, 3. Rule 1 is expand leaf. Okay, rule 2 is branch, and rule 3 is already exist. Okay, so there is actually a chance in your final exam where you show it step by step. Your exam question actually asks you what is the rule being applied at every step. There will be a chance. Okay, so make sure you know what are the three rules. The first rule is to expand your leaf. Second rule is to branch, and third rule is the substring or the suffix already exists. Okay, you also may be asked about the 4 streets, right? But your 4 streets are usually some of your explanation, and I'm going to apply your 4 streets over here as well. Okay, so let's begin from the root. Okay, let's use a black. Okay, our I will be here and our J will be here. Okay, so when my I is 1 and my J is 1, I begin here. I'm going to use rule number 1, okay, to expand it, right? So because, no, I'm going to use rule number 2 because I'm branching out for my root. So each time I branch, I'm going to create a new leaf, right? So instead of drawing a circle for a leaf, I usually like to use a different symbol, right? So if you have ever followed my tries or trees from 2004, I usually use a different symbol to denote what is my leaf. Okay, and my alphabet will be A. Okay, so a nice thing is each time you apply rule number 2, right, I want to save the number J, right? Currently my J is 1 in the leaf itself. Okay, and here, because I'm using my global N, it will be 1 and I, right? So it will automatically grow and expand based on my rapid leaf extension. Okay, which is your street number 1 in my explanation. Okay, so after I finish my phase number 1, and because I and J is at the same position, okay, I'm going to increment my I and J at the same time. So when my I increment, my I is now 2, automatically I'm looking at alphabet 1 and 2, right, which includes A and A. Okay, so here is for my street. For my second one, I realize, right, the alphabet is A, my alphabet only is A. Okay, so because my alphabet only is A, for my root, I have an alphabet A, it is rule number 3. Whenever it is rule number 3, I'm going to leave my J at the position it is at and only increment my I. Okay, so when I increment my I will look at the next alphabet after my pointer. So if you remember my explanation in my Ukkonen, right, you're going to have your active node, right, active H, and active, not active, and length. Okay, so my root is my active node, right, my root is my active node. What you see here is my active H, and my length will be 1 because my pointer is at the first alphabet A. Okay, so a nice thing about using Ukkonen is, right, if you make use of such a pointer is, instead of beginning again and try to figure out AB, right, I instantly look at the next alphabet, which is my B, right, which is the alphabet here. Here, my next alphabet is, okay, here my next alphabet is A, whereas I'm looking for B because it's AB, right, AB, but I only have AA, means I need to apply rule number 2 and branch out. Okay, so I'm going to branch out over here, AB. Okay, so the trick is, right, because my length is 1, I'm going to follow over here will be 1. My leaf over here is going to go all the way down. Okay, so here will be my node. Okay, blah, blah, blah. And here I'm going to maintain the number 1. Okay, and then because I create here will be good I. Okay, because I follow the active node and the length plus 1, right, or you can make use of your I and your J pointer to actually know what are your numbers. It's very simple. I'll let you figure it out. Okay, where each time I create an internal node, make sure you have a suffix link back to the root. Okay, so this is my suffix link back to my root. Okay, and because my alphabet is B, right, I need to create a new, right, I need to create a new one, right, which is B, right, and here will be 3I. Okay, and once I finish, okay, I increment my J. So when I increment my J, I go back to my active node, which is what you see here, and I look for alphabet B. Oops. By the way, my J was actually true earlier. So here where I made my leaf is going to be true. Okay, so I go back to my active node, which is here. I look for alphabet B. No alphabet B means it's rule number 2, and I will branch out with a B, right? And here it's going to be 3I. Okay, I finish my phase because my I and my J is at the same position. Increment my I, increment my J, right? My alphabet will be C, right? So because of my street number 1, C automatically expand, and here my active node is here my root. Do I have an alphabet C? No alphabet C. Branch out and put a C, right? And my C is going to be it will be 4I. Okay, and then I just realized I left this out again. Just now it will be 3. Okay, then here when I branch out, it's going to be 4. Okay, so at the leaf itself, it will always follow what is my J, right? So my J will be 1, 2, 3, 4. Okay, and I finish with a rule number 2. So once again, I and J is at the same position. Increment I, increment J. My alphabet will be A, right? So my rapid leaf extension automatically adds in my A. Okay, then I'm left with a substring of A. My substring of A for my active node, right? I look for A, I realize my A exists. Okay, my A exists is rule number 3. Because it is rule number 3, J doesn't move, right? I plus 1. Okay, then I look for the next alphabet, which is B, right? So what is my next alphabet? My next alphabet B actually exists. And because my alphabet of B exists, okay, my pointer will now be pointing here. So here is my active node, here is my active edge, and my length will be 1. Okay, so it reduces the need for me to traverse from the root over and over. Okay, so because B exists means it is rule number 3, which is my showstopper. Okay, my I is going to increment again, right, which is what you're going to see here. Okay, so for my pointer is my next alphabet A, my next alphabet is C. I do not have any A. Because it's C and I do not have any A, it will be rule number 2 again. I need to branch over here, right? I need to perform a branch over here. So before I branch, let me just finish off my leaf extension first. Okay, BA, 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 BA. Okay, so let me just tidy it up a bit. Here will be Q1. Okay, then here is where I'm going to branch. Okay, let's put my B here. Here will be 3, 3. Right, here I will follow my J, and my J is actually at position number wait first. No, I'm not following my J. Here will be 4. Okay, and then I will branch out over here. Right, my alphabet will be A. Right, so here will be 7, 7. Right, which is 7I. Right, my J is currently 5. Okay, so here I'm already finished with ABA, right? ABA. Okay, and because my J is 5, I'm going to mark my leaf over here as 5. Okay, and because I create an internal node, link up my internal node to my suffix. Link up my internal node with a suffix link to the root. Okay, but remember my active node is here. My active edge is here, right, which I perform a branch. So I've already finished my phase over here. Once I finish my phase over here, increment my J, right? So my active node is here. I'm going to follow the suffix link of my active node to the root. Okay, then at my root, I'm going to look for BA, right? But because I already have an active length of 1, I will instantly come to here. Okay, let me just erase it. Okay, and I will look at the next alphabet, which is C, which is not my alphabet A. Because it's not my alphabet A, I need to once again perform a branch. Okay, so let me branch it. B, C, A, B, no, there's no B, right? So it's going to branch at over here, right? So it will be C, A, B, A, C, A, B, A. Okay, draw the one here. Okay, this is 3, right, which is the same. So here, instead of 3I, it's going to be 3, 3. Okay, and here is going to be 4I. Okay, and this is where I will branch, and this is what I'm going to see. Because I create an internal node, make sure I link it back to my root. Okay, make sure I link it back to my root. And since they are in the same phase of I, And in the earlier phase, I've created my internal node. I will now need to link my internal node of the same phase but previous iteration to my current intermediate node. Then finish off with my BA, which is what you see here, right? So it will be A, it will be 7i, right? My J is 6, so I'm going to put a 6 over here. Okay, and I'm done here. Remember my active node is currently here, right? Then I increment my J and my A is at the same position, so I'm going to look for A, and then my pointer stops at here because it is rule number 3, okay, which means it have already existed. And I'm finished. So what you see here is what we call your implicit tree, right? What you see here is what you call your implicit tree. The numbers which I add over here, okay, your 1, 2, 3, 4, 5, and 6 are actually your suffix ID, right? My first suffix will be A, B, A, C, A, B, A. A, B, my bad. A, B, C, A, B, C, A, B, A, right? Is my first suffix. My fourth suffix is C, A, B, A at position, my fourth suffix, C, A, B, A. So if I move from here, it will be C, A, B, A, number 4. Okay, so the numbers which I put in each time I create a leaf corresponds to my suffix ID, which is what you see your suffix tree is. But if you notice, number 7 is missing. 1, 2, 3, 4, 5, 6. Number 7 is missing. Okay, and the reason why it's missing is because it is an implicit tree, right? So if I want to convert into an explicit tree, I need to put in my dollar sign, which is for position number 8. Okay, so just now we saw it act as rule number 3, right? So if it's rule number 3, maintain my J, increment my I. Okay, here is where my pointer, okay, and because it's a dollar sign, I will automatically do my fast extension, right, because of my global end. Okay, dollar sign, and my dollar sign, right? My fast extension, which is what you see here. Okay, then I want to look at the next alphabet after my pointer, right? My next alphabet is either A or B. Is it the same as my new alphabet, which is my dollar? But because it is not the same, means it is rule number 2. Rule number 2 means I need to branch. But since I already have an internal node, I can just branch it over here. Right, so here will be my dollar sign, and here is going to be 8i. Okay? And because my J is 7, I'm going to put the number 7 here. So if you think about it, my 7 suffix is A dollar sign. A dollar sign, number 7. Right, so here is where my number 7 is going to exist. Then increment my J is at position 8, which is only my dollar sign. My active node is my root here, so I'm going to expand, my last one, which is over here. Okay, here will be number 8, and here will be my dollar sign, here will be my 8i. Okay, so what you see here is now an explicit, okay, suffix tree, right? Or the suffix tree which you have learned in FIT3004. Okay, so it seems like it's a very, very long process because I'm explaining. Let's see how fast I can do it now very, very quickly. Right, so let's go A, B, C, A, B, A. Okay, let's color my root differently. Okay, So the first one is only A, right? 1I, right? Second one is AA, my pointer is here. Third one is AAB, okay? Then I realize my next alphabet is B, which doesn't exist. So here I'm just going to convert it very quickly, right? Into AB. Here will be QI. So a trick is to put numbers here to help you easier to observe, right? So here my number is 1, here will be B, okay? Then I'm going to punch out a B, here will be 3I, right? Change the number here to 1, and here my J is at position 2. Then finally Q1 for B, which is 3I, okay? And here my pointer will be 3, okay? Then the next one will be C, okay? Put in C, 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 create a new one, which is only for C, which is C. Oops, my C should be below, and here should be 4I, okay? Next one will be A, add in of my A's, okay? Then I have a A which is pointing here. Next one which is a B, already exists, B, 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 B. My pointer is now pointing here. Next alphabet will be A, okay? So now I'm looking at A, right, adding the A, okay? But my next alphabet doesn't have a B, so I'm going to put a B here, break this off, put here as 3, 3. Here will be the next number, which is my 4, right? Break this off, put this as a 7I, okay? Draw my suffix link, okay? This is my suffix link. Then the next one will be BA, B, I need to branch here again, B, erase here, branch here, 3, 3, 4I, right? Here put in a, which is 7I, okay? Then my last one will be over here, which is only my A, which is 7I, right? I forgotten here should be 5, here should be 6, and here should be 7. Okay, so you can actually do it relatively fast, right? The more you practice, the faster you're going to be. Okay, so let me just erase off my word. So it's quite a simple question, and such a question is usually worth around 4 to 5 marks, right? Where you're going to have like you're going to have 1 to 2 marks about your suffix link. You're going to have another mark about all of your leaves, saying some of the branches and stuff, right? So the way we usually mark is as each of the suffix which you put correctly is usually worth some form of marks, like 0.5 or something. Then your suffix link is usually worth like 1 mark or so. Okay, so it's quite a simple question usually, right? And it's something which you can practice for your exam. So it is not a question you're supposed to miss out if you want to score well in your exam. And it's historically because I did look at the exam paper which failed for remarking and so on. Okay, the ones who fail the exams are the ones who leave such a question blank, right? And not many people fail the exam. Okay, but the ones who fail it are the ones who leave Ukkonen blank. So it's a question which, if you want to pass the exam, you should never leave it blank because you can practice for it. Okay, now let us finish off the rest of the question. Okay, look, how can I use my suffix tree right? So if you notice here, it says suffix 3. It doesn't mention implicit or explicit. Usually, it will only work if it is explicit. Implicit doesn't actually work, right? Implicit is just compressed. Only your explicit 3 can be used to solve off the question here. Okay, so to find the substring, to find the suffix, to find the number of times it occurred, to find the smaller substring exactly k times, longest repeated substring, lexicographically the smaller suffix, and to find the suffix array. Okay, so let us go through it one by one now. Okay, so let's use blue as a given color, right? And let me open my question here side. Okay, the first one. Okay, substring. How can I use a tree to find a substring? Okay, so for example, you know a substring is actually the prefix of suffix. What we see over here, whiteboard. What you see over here is already a suffix tree. So we already have the suffix component. Okay, so the prefix component is just us traversing. Right, let's say my substring is actually AB. Right, so I can see a substring here which is AB and another substring here which is AB. So if I begin from my root and I traverse A, B, if a path exists in my tree, means I've already found my substring. Okay, let's say I'm looking for a substring which let's say is AC. Right, so if you see here, I do not have any AC as well at all. So I begin from here, A, right, I got A dollar, A, and AB. You realize I do not have AC. If a path doesn't exist, right, means a substring doesn't exist, right? So it is something which is very, very, very useful. Okay, so if you came from a point of your assignment question number 2, if you get the entire string and you build a suffix tree, right? So you use Ukkonen with all of the suffix array, right, to build a suffix tree, right? Put in your dollar sign for it to be explicit, right? And then you program some form of traversal, right? You should be able to solve your question number 2 in linear time, because your traversal will be O of M, building the tree is O of N, total complexity is O of M plus M. Okay, but sounds easy, programming it is going to be very, very long. Okay, my next question is to see if a suffix exists. Okay, so let's say my suffix is AB, right? So we saw earlier that the substring of AB exists, right? But you realize AB is not a suffix because it doesn't end at the back of the string. Okay, so how are you supposed to know if it's a suffix? It will be a suffix if I end with a dollar sign as my next alphabet. Okay, so let us try with AB. A, okay, B, right? I've reached here. Okay, AB. My next alphabet is A and my next alphabet is C, right? A and C. You realize it doesn't end with a terminal. Because it doesn't end with a terminal, you know it is not a suffix anymore. Okay, let's try ABA as a suffix, right? As you will see here, ABA, right? So A, B, A. Okay, so I have a path of ABA. After I've traversed my path, I need to ensure the next alphabet is a terminal, which is a terminal, which means it is a suffix. That's all, right? So it is very simple and it's really, really useful. Okay, so I've finished A and B. Okay, let's move on to C. C. Oops. Okay. C. Find the number of times a swing key occurs as a substring. Okay. So earlier we saw we have A and then B. Okay. The question now wants is number of times, or let's just call it frequency of substring. Okay. So let's say I look at substring of AB. Okay. So I will traverse A, B. Right. So let me just erase this string. Okay. So if I were to traverse, let's use blue. Let's use green. Okay. A. Right. So I traverse A and then B. Right. I know my substring actually exists. Okay. If I want to know the frequency, the best way to know my frequency is to count the number of leaves. So below AB, I have how many leaves? I have one leaf, which is 5, and another leaf, which is 2. Right? Because if you see here, I have AB, I have AB. Right? So I'm going to have a substring which begins with AB. Right? I'm going to have another substring which begins with AB. Okay? So I'm just counting the number of substrings which begin from AB. So the trick is to traverse the substring. Once you reach the end of your substring, perform a recursion and count the number of leaves. Right? Count number of leaves, right, using recursion. Okay? So let's go through another example. Let's say instead of AB, my substring is only A. Right? You realize my A occurs 1, 2, 3, 4. Right? 4 times in my original string. How am I supposed to know it? I begin from here, I go to A, I reach the end of my substring. How many leaves is under A? Right? I have 1 leaf, I have 2 leaves, I have 3 leaves, I have 4 leaves. Right? So I know the frequency is 4. Right? I got 4 substring of A, or more specifically, because substring is a prefix of a suffix, I got 4 suffixes which have a prefix of A. Right? So this is your C, which is very, very simple. Okay? D. Okay? Find the smallest substring which occur k times. Okay? So we can have a lot of substring. We have CA, BCA, BA, BA, and so on, and so on, and so on. Okay? So let's say I want substring which occur 2 times. Substring which occur 2 times, I have multiple options. You can see B, right? You can see B actually occurs 2 times. You can see AB occurs 2 times. Right? And the question wants the shortest, so my answer needs to be B. Okay? So what I can do is the following. Okay? I can perform a recursive traversal that goes to the leaf. When I return for my leaf, I return a number. Okay? So let's say my first recursion path is I go here. Okay? I reach a leaf. So on the way back over here, I will put the number 1. Okay, I will put the number 1 because I've passed by 1 leaf. Then as I return back to here, I'm going to come down here. I see another leaf. So when I return, I will plus 1. Okay, so here my number is going to be 2. Then here I will go here. Right, I have 1, it will be 1, return, come back here, my number will be 2. Okay, then when I return here, I will get my 2 and I will plus it up, it will be 4. It's the same as what you see in your FIT 1008 to calculate the gap, to calculate the number of sugars and stuff. So what I'm doing here is I'm counting the number of leaf, right? And I save it at every node. This node have 2 leaf, this node have 2 leaf, my node here have 4 leaf, my node here actually have 4, 2, 5, 6 leaf. Right, is it 6 leaf? No, it's 8, right? 1, 2, 3, 4, 5, 6, 7, 8. I can do maths. Okay, so here will be 8. Okay, so it denotes off the frequency. If I want the smallest substring which occur at least k equals to 2, okay, I will look for the smallest, right? So here is 2, here is 2, but which one is smaller? If you look at the gap, right, here actually goes through 1 alphabet, 2 alphabet. Here actually only goes through 1 alphabet. How are you supposed to know it is, right, you're not supposed to count the edge. You're supposed to sum up all of the length. Okay, so if you see here, my length here is 1, 1. Right, I start at 1, I end at 1, so my length here is actually 1. Okay, I start at 3, I end at 3, my length here is actually 1. Right, I start at 3, I end at 3, my length here is actually 1. Okay, but my length for my root will be 1 plus 1, which is 2. Okay, and my length here will be 1. So here my distance will be 2. Here, right, my length here 1. Here my length will be 4. So my total length is 1 plus 4 will be 5. Okay, so your question here was actually a past year exam question. Describe how you can find the shortest, longest substring, right, blah blah blah. Okay, so here you want to choose the node with the smallest number, right? So here my node is 1, here my node is 4, here my leaf, which is also a node, is 5, and so on and so on, right? So please do not assume one edge is 1, right? You want the length of the edge because it is a suffix 3, not a suffix try. So if we were to compress it 1, 2, 3, 4, 5, 6, 7, my length is 7, right? Because I have 7 alphabet, not the number of edge. Okay, so let me repeat the answer in full now. Okay, let me just erase everything properly. Okay, k equals to 2. Number 1, use your recursive traversal, which will traverse through your entire suffix tree, right, and save at the internal node, okay, the number of leaf. So now I have the number of leaf below each and every node, and you know from question C, it corresponds to the frequency. So we will look for the internal nodes with the number 2, which is the one here and the one here. Okay, but because we want the shortest, we want to calculate the distance from the root. So here, because I start at 3 and at 3, I have a length of 1. So distance from the root is 1. Here, 1, 2, distance from the root is 2. And because I want the smallest or the shortest, means my substring will be B. Okay, so guess what your question number E is. Then if I were to move on to question E, right, I want to find the longest repeating, oh my god, I'm actually slacking, right, longest repeating substring. You know a substring repeat if it have a branch, right? As long as it have a branch, it means it actually repeats itself. Okay, so if we want the longest, means we want the furthest from the root. Okay, so in other words, to find the answer is you are going to find the deepest node, right, or deepest internal node, right, because internal node have a branch. You want the deepest internal node. right? What is the deepest? As what I've mentioned before, right? The maximum length from root, right? Please do not write number of edges from the root. Maximum number of edges is wrong, right? Partial exam question, half of the Malaysian class got it wrong because they explain it as the number of edges, okay? But 80% of the Australian campus explain it as the number of edges, which is even worse, right? So remember maximum length from the root. When I say length, means the number of characters, right? Or the number of alphabets. This is what your A is. Okay, so let me finish it off. Okay, the next question will be F. Okay, find the lexicographically smallest suffix of my string. Okay, so lexicographically means alphabetically, right? A will be smaller than B, will be smaller than C, will be smaller than E, smaller than X, smaller than Z. And you know the structure of a trie, right? Because when you implement a node in a trie, right? When you implement a node, you're going to have a H array, right? Which is from 0 all the way to 255. Okay, so 97 is going to be for A, right? 98 is going to be for B, 99 is going to be C, and so on and so on and so on, right? So what you want is you want to look for the lexicographically the smallest one, and lexicographic, in other words, if the alphabet doesn't exist, it will be a none, right? If it doesn't exist, it will be a none. If let's say A doesn't exist, it will be a none, right? So position 97 is going to be a none. But let's say alphabet B exists. Because alphabet B exists at position number 98, it will be another node, right? So you're going to strive always to prioritize the leftmost position of your H array, right? So if I begin from here, what is my leftmost, right? My left, I got A, dollar, right, which you ignore, A, B, and C. My leftmost is going to be A, okay? And then, what is my leftmost? My leftmost will be dollar, A, B, and C. Only in the first one, we will ignore our dollar sign, right? Only from the root, we ignore a dollar sign because an empty suffix is automatically, lexicographically, your smallest. Okay, so here, right, if I were to look at my arrangement, technically my dollar sign should be at the negative one, right? A special one, right, which is the leftmost. Okay, so my lexicographically the smallest alphabet is going to be A. I mean my lexicographically smallest substring is going to be A. Right, always strive left until you reach a leaf. Okay, what happens if I change my question now? I want lexicographically the biggest, right? If it's the biggest, always prioritize the right. So begin from my root, I got A, right, I got B, and I got C. Which is the biggest? It will be C, right? Then when I reach L, you realize I've already reached a leaf, right? There's no other branching, so it's the rightmost. Therefore, it's C, A, B, A, other side. Okay, so the answer is, okay, look for the leftmost leaf. That's all, right? A very, very simple question. And the last and final question, right? G. How to find the suffix array? So I've already explained it in my Ukkonen earlier. Since we have already built our very nice Ukkonen explicit tree, and I know the leaf corresponds to the suffix ID, I just need to traverse it in order, means from left to right, right, in order. Okay, so what is my suffix array? Okay, number 1, the leftmost is dollar sign, so it will be 8. Then the next one will be A, dollar sign, 7, come back here, A will be 1, come back here, AB, where's my B? AB, right, BA, 5, because I always prioritize left, then I go right, which is school, go all the way back up here, right, can prioritize left again, which is 6, can go right, right, because this is C, this is 3, go all the way back and go right, which is 4. You realize I already have a suffix array. So how can you find a suffix array from Ukkonen? Very simple. Number 1, right, make a suffix, I'm lazy to write. Number 1, make a suffix tree, right? Each time you have a leaf, right, because of rule number 2, make sure you put in the position J as the leaf. Okay, then convert your implicit to suffix tree to ensure all of the leaf actually exist. Once all of the leaf exists, perform an in-order traversal, which means you recursively always go left, followed by right. The leaf which you visit in order, the number which you save at the leaf, they are suffix ID. But since you're traversing in lexicographical ordering, right, the ordering of your suffix ID is your suffix array. Once you have your suffix array, right, you can use it for PW key, you can use it for your assignment question number 2 as well, where you use your suffix array for searching and so on and so on and so on. Okay, and note, maybe I won't explain it here. If you remember, okay, I might explain. If you remember from your assignment briefing, I gave you good complexity, okay, and O of n plus m, okay. There is an even faster one, okay, and once the assignment finish, or if you submit your assignment, I will share out what is the fastest algorithm of all. Okay, the fastest algorithm is a research paper. Okay, and it's quite a complex one. And that's all. So hopefully I'm helping you out with your Ukkonen, right? And hopefully you understand your Ukkonen. As a final recap or summary, okay, please learn to draw a suffix tree with Ukkonen step by step, alright, using all of the rules, using all of the tricks, and always include your suffix link. Make sure you read the question carefully if it is implicit or explicit as well. Okay, and as a follow-up question, you're going to be given one of such questions usually. Okay, please explain. Right, given a string, how can I find the suffix? Given a string and a pattern, how can I find it? Right, how to find a suffix array from a string with a suffix tree, blah blah blah. Right, all of these have been historically coming out every semester of your final exam. And if you were to ask me honestly, if your exam is going to be open book, such questions will be the best question for us to ask, right? And just a note as well, Arun actually made the exam paper with Anuja's input. Both of them will never share your exam paper with me until the exam paper is finished. Okay? So what I'm telling you is just my understanding of Arun and understanding of the syllabus. Right, if it's not coming out in the exam, it's not my fault. Okay, that's all. I see you guys around. Bye.